Okay, this is from the test that you had, the sample test, Eric, that you had, and this is question 14, and I'll put 15 in another video. What you're looking at right here, of course, is an integral, and then here you're looking at doing the derivative of that integral. So you need to, as we talked about, need to understand the notation and what it's meaning. Well, of course, integrals and derivatives are sort of like inverses. They sort of opposite ends of the spectrum, differentiation and anti-differentiation. And so, from one perspective, I suppose you might think, well, aren't they really asking me to do something and then undo it? And so, isn't the whole thing just moot? And it sort of is. That's one way to think of that. Um, but instead, I'm going to propose a different idea for you. When you do this integral right here, uh, one concept that the integral can embrace is that of area, right? So if you have some some function, and one way to look at that integral from a point A to a point B over which the thing is defined is to think of that area in there. All right. Well, what they're doing in this case is they're holding one piece of the one of the bounds constant. They have a 5 here that's constant, right? And they're allowing the other bound, the lower bound in this case, to float. So they're saying this is like x, where the a is positioned here, and then this is 5, all right? And so they're allowing this lower bound, this lower endpoint, to be moved, right? Now, when you put that inside the construct of the derivative, the essence of this question, derivative, right, it means a lot of things too, but one of them is rate of change, okay? So what this is measuring is the rate of change of the area, all right? In other words, as we move this lower bound, what happens to the area underneath the curve as you approach, as you come in towards that upper bound. So that's the idea that you're looking at there. And what this has to do with is the second fundamental theorem of the calculus. And so let me take a moment to tell you what the second fundamental theorem of the calculus says. Um, and it's based on the mean value theorem for integrals, so you can look up those two ideas. Um, what we're what we're talking about is the second fundamental theorem of the calculus, and what that says is if you have the derivative with respect to some variable um, with bounds, and one of the bounds is a variable, and the other bound is a constant. And in particular, the lower bound is a constant, right, of some function. Then all you need to do, some function in terms of a different variable, that should be a t right there. Then all you need to do, because the integral and the uh, derivative are inverse types of operations, all you need to do is replace the variable by um, that other that other variable. So the t gets replaced by the upper bound x, and so that becomes f of x. And if you say, well, what about the lower bound constant? Well, think about it for a second. What's the rate of change? What's the rate of change of a constant? And of course, the rate of change is a constant. We know that when we evaluate the integral, we do upper bound evaluation minus lower bound evaluation. Um, but of course, when you're measuring the rate of change of that, that's going to be a zero. So that's sort of the idea. It's the fundamental theorem of the calculus that they want to employ here. And so I'll go back to your test here and take a look at what we want to do. We have a little bit of an issue because notice the lower bound is the variable. Well, to use the fundamental theorem of the calculus, it can't be that way. When you have your problem, what I just wrote on the other page, I had the variable up here, and I wrote the word constant down here to indicate that your lower bound has to be the constant for whatever particular function you're talking about. Right? So the first thing I'm going to do, I can use a little integral rule to reverse these bounds. And all that I have to do is change the sign. And this is a positive, so I'll make it a negative. And that will allow me to change those bounds. So the 5 is now the constant lower bound, and the x is now the upper bound. And everything else is going to just stay the same. So maybe you want to stick that away in your memory. Um, if you want to reverse the bounds for a particular uh, expression, you can do that. You just change the sign. And of course, this was positive, so I made it negative right there. Now, the second fundamental theorem of the calculus says all I have to do is replace the x, the t rather, by the x, by the upper bound. So that's going to become, and of course we do have a negative out in front, it's going to become an x plus rad x, right? Underneath that radical sign. Well, don't forget, you got to have the dt, right? You got to have the rate of change of t. And so that, what you're going to put in there is the derivative of that upper bound variable expression. So if you had f of x equals x, what would be f prime of x, right? What would be the derivative of that x? Well, that would be a 1. So this dt right here gets replaced by a 1, right? And so there's your answer. There's the rate of change of the area underneath this curve um, as one of the bounds is allowed to slide. And so there's your answer at choice B. All right, so that's question 14, and I'll be back in a minute and do question 15. Um, so just a quick review here. You're doing the fundamental theorem of the calculus. You have to have a constant lower bound, um, and you merely replace the variable in the expression in the function by whatever variable they're using for the bound, and it's got to be the upper bound. And then you have to remember to do the derivative of that variable bound, of that variable expression. Okay? And in terms of a concept, what you're basically measuring is the rate of change of the area under a curve. At least I think that's the easiest way to think of it. Hope you found that helpful. And like I said, we'll be back in another video with the question 15.